In the vast silence of deep space, beyond the familiar planets and even beyond the frozen realm of the Kuiper Belt, something enormous has begun a slow and silent approach. It is not a spacecraft, not an asteroid, and not a typical comet, at least not in any conventional sense. It is a traveler from the outermost edge of the solar system, where the sun's light is barely a whisper and temperatures plunge toward absolute darkness. This massive visitor is known as CR 2014 UN 271 Benedinella Bernstein, or simply BB. It is a name that has quietly stirred excitement across observatories, universities, and research teams because BB is unlike anything we have seen in modern astronomy, and its sheer size alone tells us that it should not behave like other comets, and yet it does. Most comets are small, fragile, icy objects, typically measuring between 1 and 10 kilometers in diameter. Some of the larger ones, like the famous Hale-Bopp, reach nearly 60 kilometers. But BB is estimated to be around 150 kilometers across, so large that its nucleus alone rivals small planetary moons. It is bigger than many known dwarf objects and far beyond the scale of what anyone expected to discover drifting inward from the outer solar system. That is why when astronomers detected it in archival sky surveys, it was immediately clear this was no ordinary comet. It was something far more ancient, something that had remained untouched for billions of years, preserved in the deep cold of space like a relic from the beginning of the solar system. And this is where the mystery deepens. Despite its massive size, BB began behaving like a comet while still extremely far from the sun, at distances where sunlight is too weak to melt even the most volatile ices. It started outgassing, releasing carbon monoxide, carbon dioxide, and ammonia, materials that had been frozen in its body since the birth of our solar system. These early bursts of activity were not only surprising, they were scientifically unsettling because they challenged what we thought we knew about comet physics and thermal behavior. The object was waking up too early, too strongly, and too powerfully for conventional comet models to explain. This is where the concept of nonlinearity becomes important. In science, not all processes are predictable. Some systems behave calmly for long periods, and then, suddenly, they transform in unexpected ways. A small change in conditions can trigger major shifts in behavior. This is true in economics, weather, and earthquakes, and it is certainly true in space. BB embodies this unpredictability. It is stable one moment, explosive the next. It is quiet in the darkness, then suddenly alive with jets and bursts of invisible energy. Its journey is not just a cosmic event. It is a scientific opportunity, a chance to observe something primordial, a frozen witness from before the planets formed, carrying chemical secrets that have never been touched by sunlight. It is a reminder that even in a universe governed by physics and mathematics, there are still surprises. In the cold, quiet edges of space, something very old has awakened. CR 2014 UN 271 Benedinella Bernstein, or BB, is officially labeled as a comet, yet it refuses to behave like the comets we have long studied and understood. Under normal circumstances, comets become visibly active when they approach the inner solar system, typically between the orbits of Jupiter and Mars. That is when sunlight is strong enough to warm their icy surfaces, triggering the familiar process of sublimation, where frozen gases transform directly into vapor, creating a coma and tail. But BB started sublimating while still at an enormous distance from the Sun, nearly 26 astronomical units away, almost at the orbit of Neptune. At that distance, sunlight is too weak to awaken most comets, yet BB began releasing carbon monoxide, carbon dioxide, and ammonia in unexpected outbursts. This early activity made scientists immediately question whether the term comet was even appropriate. The gases released, CO2, and ammonia, are volatile compounds that sublimate at extremely low temperatures. Their presence reveals that BB is made of pristine material, untouched since the formation of the solar system. Most comets that make repeated journeys near the Sun lose these fragile compounds long before we observe them. But BB has likely never been close to the Sun, meaning its chemical makeup is ancient, unchanged, and primordial. It may be one of the purest surviving samples of the early solar system, still carrying the ingredients that built planets, moons, and other worlds. When compared to the recent interstellar visitor 3I Atlas, BB is far larger, far older, and far more mysterious. 3I Atlas drew attention because it came from deep interstellar space and displayed odd jet structures. But it was small, just a few kilometers across, and behave more like a typical comet passing through the solar system. BB, in contrast, is approximately 150 kilometers wide, making it nearly 30 times larger in diameter and thousands of times larger in volume. It is closer to the category of dwarf planets than comets, and yet it is actively outgassing and erupting like a comet, even while far from the sun. This dual identity, a comet in behavior but a planetary-class body in size, makes it profoundly unusual. Its enormous size also has physical consequences. Unlike small comets, BB has a measurable gravity field. When its sublimation begins and material blasts away from its surface, some of that material may fall back, unable to escape its weak but real gravity. This could produce complex and unpredictable coma structures, or even a temporary atmosphere unlike anything we have observed from inactive cometary bodies. No comet in history has combined this kind of size, behavior, and chemical composition. Scientists hesitate to label it because it defies traditional comet definitions, but it also doesn't fit the category of a dwarf planet, centaur, or asteroid. It is possibly a new kind of object altogether, a preserved relic from deep space, made of ancient solar system ice and rock, large enough to hold itself together, and active enough to challenge the physics of cometary behavior. It is not just a comet. It is a time capsule, a massive, mysterious, primordial object drifting toward the light, carrying secrets from the birth of everything we know. Right now, see our 2014 UN 271 Benedinilla Bernstein, or BB, is silently moving through space near the orbit of Uranus, drifting slowly inward toward the region of Saturn. It is not rushing in like typical comets, which often enter steep, elliptical paths toward the sun. Instead, BB follows a vast, sweeping trajectory that brings it only modestly closer to the sun, never fully entering the inner solar system like most comets do. Its closest approach, or perihelion, is predicted for January 2031 at a distance of approximately 10.95 astronomical units. That places it near the orbit of Saturn, a distance where most comets would remain frozen and inactive. Yet BB has already shown signs of activity, releasing gases and dust even at extreme distances. This makes its journey uniquely intriguing because it challenges current models of how comets behave at such cold, distant regions. What makes this even stranger is that almost no major comets remain active that far out. Typical comets begin to sublimate as they cross the orbit of Jupiter or Mars, where sunlight is strong enough to vaporize ices. But BB is erupting at distances 2 to 3 times farther away, displaying volatile sublimation while barely warmed by sunlight. At these distances, solar radiation is too weak to trigger normal thermal activity, yet BB responds dramatically, behaving like an awakened object, alive with chemical volatility. This means its composition is unlike anything we typically study, likely containing deeply preserved primordial material from the earliest formation of the solar system. Another key feature that sets BB apart is its orbital inclination. Most comets and planets orbit roughly within the same flat plane, known as the ecliptic plane. But BB approaches at a jaw-dropping 95-degree inclination, meaning its path is nearly perpendicular to the planetary plane. Instead of gliding across the flat solar layout like most objects, it is slicing through the solar system vertically, moving up and down through space like a cosmic elevator rather than circling like a disk. This kind of orbit is extremely rare, and it makes BB's movement highly unusual, both visually and dynamically. During the current years, around 2025 and 2026, BB appears directly underneath the solar system. In astronomical terms, this does not mean below in a physical sense, but below the plane in which all major planets orbit. Imagine the solar system as a flat table, and BB passing several feet beneath it. This unique positioning creates interesting planetary geometry, as BB aligns with planets and the Sun not along the horizontal axis, but vertically, creating square-like energy angles and gravitational interactions. While this does not imply mystical effects, there is scientific interest in how large objects passing through different angles might interact with the solar system's gravitational, electromagnetic, and plasma environments. Planetary geometry is the study of how objects align across space, not just in terms of distance, but also in terms of directional orientation and angle. Object positioned directly above or below the ecliptic plane can produce different observational perspectives, different gravitational influences, and potential differences in how solar radiation reaches them. BB's vertical passage through the space gives astronomers a rare opportunity to observe how a large, active, primordial body behaves as it moves through unusual angles of solar influence. It is not just where BB is, but how it is moving through space that makes it one of the most intriguing cosmic visitors of this era. Comets typically begin their transformation as they enter the warmer regions of the solar system, usually between the orbits of Jupiter and Mars. That is where the sun's energy becomes strong enough to heat the icy surfaces of these small bodies, causing frozen materials, mostly water ice, to sublimate into gas and form a glowing coma and tail. This is predictable behavior, seen countless times with comets like Halley, Hale-Bopp, and Neowise. They brighten as they approach the sun, become active, and then fade away once their stored surface ices are exhausted. Their behavior follows a pattern, and their light curves, while sometimes fluctuating, generally align with thermal modeling. But Bernstein, or BB, clearly did not receive this memo. Instead of waiting until it was warmed by the sun, it began showing activity while still 26 astronomical units away, near the orbit of Neptune. At that distance, sunlight is only 1,000 as strong as it is near Earth, making it far too weak to melt common cometary ices. Yet BB was releasing jets of carbon monoxide, carbon dioxide, and ammonia, all substances that vaporize at extremely low temperatures. These are volatile ices that are normally long gone by the time a comet makes repeated visits to the inner solar system. But BB has likely never been close to the sun before, meaning these substances have remained frozen since the birth of the solar system. As a result, it is behaving like a living fossil, preserved in deep cold for billions of years, now displaying its ancient chemistry for the first time. It did not just begin sublimating, it erupted. Its outbursts were powerful, ejecting millions of kilograms of material into space in short bursts. Observers have noted that BB's light curve is erratic, unpredictable, and chaotic. Most comets brighten steadily as they approach the sun, but BB flickers, flays, and dims in unexpected ways, responding to temperature changes and solar influences with nonlinear reactions. At times it shows clear activity, while at other moments it appears silent, as though conserving its energy or struggling to release trapped volatiles. The key word here is nonlinear. Normal comets follow relatively linear thermal behavior. More heat equals more activity. But BB is displaying behaviors that jump, surge, and collapse without clear triggers. This suggests that its internal composition and structure may be unusually complex. Perhaps trapped pockets of ancient gases explode when cracks form in its crust. Perhaps its gravity, unusually strong for a comet-sized object, is affecting how material escapes or falls back. Or perhaps its surface is layered with different ices that respond in bursts, not gradually like most comets. This unpredictability makes BB extremely difficult to model. Scientists cannot confidently predict its brightness trends, its sublimation rate, or even how stable its orbit will remain over time. Some even suggest that as it gets closer to the sun, its outgassing could create measurable non-gravitational acceleration, subtly altering its path in ways we cannot foresee. In short, BB is not behaving like a comet. It is behaving like a nonlinear system, sensitive, reactive, and capable of surprising us all. In this sense, BB is not just an object, it is a reminder that space is not as predictable as we sometimes believe. It is a living demonstration that the universe still holds secrets, even in the coldest and most silent places. When we compare comets, we often begin with well-known names like Halley's Comet or Hale-Bopp. Halley's Comet, one of the most famous in human history, measures about 11 kilometers across. Hale-Bopp, one of the brightest and most spectacular comets ever observed with the naked eye, is much larger at around 60 kilometers in diameter. Both produce impressive tails and comas when they approach the sun, yet both remain small when compared to something like Chiron, a 220-kilometer icy body classified as a centaur, an object that shares characteristics of both asteroids and comets. Chiron is not counted as a traditional comet, but it can display cometary behavior, including an occasional coma. But see our 2014 UN 271 Bernstein, or BB, enters an entirely different league. With an estimated diameter of around 150 kilometers, it is much larger than Halley and Hale-Bopp and only slightly smaller than Chiron. Astronomers now describe BB as the second largest cometary object ever discovered. Its nucleus alone could swallow both Halley's Comet and Hale-Bopp several times over. To visualize this, imagine Earth as a basketball. Halley's Comet would be a grain of sand. Hale-Bopp might be a pebble. BB, however, would be the size of a golf ball, tiny compared to Earth, yet enormous compared to nearly every comet we have ever studied. Its large size introduces conditions that normal comets do not experience, most notably, the presence of a measurable gravitational well. Typical comets are so small that when gas and dust erupt from their surfaces, they are lost to space almost immediately, forming long, elegant tails. But BB is large enough that some material, especially dust grains and heavier particles, may not escape entirely. Instead, some may fall back, creating a shallow cloud or halo of material that behaves differently from the traditional cometary tail. This recycling of ejecta is something rarely seen with comets and is usually only considered in objects with strong gravity, like moons or small dwarf planets. BB's gravity also affects how its coma evolves. Instead of forming a simple, expanding cloud, the gas and dust may be partially contained, forming layers, rings, or irregular structures. This could lead to complex coma dynamics that do not follow standard comet models. It may even temporarily collect its own dust into orbit-like structures before releasing them, creating behavior more similar to an active minor planet than a typical comet. The significance of BB extends beyond its size. It is what astronomers call a primordial object, meaning it has preserved materials from the earliest days of the solar system. Most comets have been heated and altered by repeated passages near the Sun, losing their most volatile ices and undergoing surface changes. But BB likely has never approached the Sun before. It carries ammonia, carbon monoxide, and carbon dioxide, materials that evaporate easily and would not survive in bodies that have been warmed even once. This makes BB one of the purest time capsules we have ever encountered. For science, this means BB is more than a comet. It is a messenger from the solar system's deep past. It offers a rare chance to study the building blocks that form planets, moons, and perhaps even the ingredients for life. Its presence reminds us that the solar system is not just a collection of objects, it is a living archive of time. See our 2014 UN 271 Bernard Bernstein did not come from the outskirts of the solar system. It came from far beyond. Its estimated aphelion distance, the farthest point from the Sun in its orbit, lies somewhere between 40,000 and 60,000 astronomical units. That is so distant that it reaches well beyond the Oort cloud, the theoretical shell of icy objects surrounding the solar system. At these distances, the Sun's gravity becomes extremely weak. The gravitational pull from the Sun is no longer dominant, and the object enters a transition zone between our solar system and the gravitational influence of the Milky Way itself. BB spent millions of years wandering in this region, where space is no longer truly solar and not yet fully interstellar. It is a borderland between systems, a place where comets are born, exiled, and forgotten. Objects traveling this far are not gravitationally stable in the traditional sense. They no longer obey only the Sun's gravity. Instead, they respond to what astronomers call galactic gravitational tides, the subtle yet persistent stretching forces created by the mass distribution of the Milky Way. These forces, while weak, gradually reshape orbit over millions of years, especially for large objects like BB. This means BB's orbit is not static, predictable, or easily calculated beyond a point. It is influenced by forces that operate on cosmic timescales, far beyond the mechanics of everyday planetary orbits. In addition to galactic tides, other events can shape its trajectory. Passing stars, rogue planets, or even wandering brown dwarfs may have nudged BB in the distant past. These interactions do not need to be strong to be significant. At distances of tens of thousands of astronomical units, even a small gravitational push can redirect an object's orbit toward the Sun. BB may have once been traveling a quiet, lonely path in deep, frozen space when a passing star disturbed its orbit just enough to send it slowly inward. That journey, initiated millions of years ago, is what has brought it to the edge of our solar neighborhood today. This chaotic nature is why BB's past and future cannot be fully traced. Unlike planetary orbits, which are stable and predictable, BB's path becomes uncertain when extended too far into the past or projected too far into the future. Tiny unknown influences compound over time, making its long-term orbit impossible to model accurately. Scientists can estimate its behavior while it is moving near the known solar system, but the deeper it travels into space, the more its journey becomes a mystery. This uncertainty makes BB profoundly interesting. It is a cosmic drifter, shaped not just by the sun, but by the galaxy itself. It represents a class of objects that are not planetary, not interstellar, but transitional and migratory, objects shaped by long timescales and distant forces. Its presence tells us that the solar system is not isolated. It is connected to the galaxy, both gravitationally and chemically, through objects like BB that migrate between the two realms. We call BB a comet, but in truth, it is a messenger shaped by both the solar system and the Milky Way, carrying the history of both. As CL 2014 UN 271 Bernstein continues its slow descent toward the inner regions of the solar system, all eyes are on January 2031, when it will reach perihelion, its closest point to the Sun, at approximately 10.95 astronomical units. This is still near the orbit of Saturn, a region cold enough that most comets remain dark, quiet, and inactive. Yet the question arises, if BB is already displaying violent activity at vast distances, what might happen when it experiences even a moderate increase in solar energy? Scientists do not have a definite answer, because nothing like this has ever been observed before. BB's behavior so far suggests that as it approaches perihelion, extreme outgassing could occur. Its surface, layered with volatile ices from deep time, may respond unpredictably to increased solar radiation. Buried gases could violently escape, pressurizing beneath its crust and bursting free in powerful eruptions. These outbursts could dramatically brighten the object, possibly making it visible even from Earth with large backyard telescopes. But its size, gravity, and chemical complexity make it capable of more than just visual brightness. Such outgassing could exert non-gravitational forces on the comet, gradually shifting its orbit. In other words, BB's own activity could subtly push it off its predicted path. There is also a growing scientific debate about how stable BB will remain as it heats up. Some suggest it could become significantly brighter and more active, possibly even producing a coma and tail larger than anything we have seen before. Others think it may remain relatively dim, its volatile material buried too deep to trigger continuous eruptions. And then there's a middle scenario, where BB becomes erratic, alternating between quiet and explosive phases, behaving as a truly nonlinear system. It could flare dramatically one week and fall silent the next, without any clear pattern. What fuels this uncertainty is one of the most remarkable observations so far. BB once released an estimated 100 million kilograms of dust, ice, and gas in less than a day. Such an eruption is extraordinary by cometary standards and suggests that trapped pockets of volatile material beneath its surface can suddenly rupture with explosive force. On a normal comet, such activity would strip material away permanently. But BB is massive enough that some ejected dust may even fall back to the surface, altering future sublimation patterns and creating a constantly evolving environment that is impossible to predict. NASA has taken a strong interest in BB, recognizing its rare scientific potential. This is possibly the best preserved relic of the early solar system we have ever seen. Its chemistry and structure could provide clues to how planets formed, how water and organic materials spread through space, and how interstellar objects migrate. Yet despite its significance, there is currently no official mission planned to visit it. Some independent researchers have proposed theoretical flyby missions that could reach BB in the early 2030s using gravity-assist maneuvers, but no space agency has committed to launching such a mission, at least not yet. As perihelion approaches, one thing becomes clear. With its ancient chemistry, unpredictable outbursts, and immense size, BB is on the threshold of revealing secrets that cannot be fully predicted, even by the models we trust. It may dim, erupt, break apart, or surprise us entirely. In this sense, BB remains exactly what it has been from the start, a cosmic question, moving steadily toward the light. The question naturally arises, could we send a spacecraft to visit CR 2014 UN 271 Bernstein and examine it directly? It is a tempting thought. Here is the second largest cometary object ever discovered, carrying primordial material from the earliest days of the solar system. It is active, enormous, ancient, and unique. And unlike most comets, which zip past the sun unpredictably and quickly, BB follows a relatively slow, long-period orbit, passing through the outer solar system at a pace that could, in theory, allow for a carefully planned mission. But so far, space agencies have shown no indication of pursuing such a mission, even though the scientific value would be unprecedented. Interestingly, a group of independent spaceflight enthusiasts and orbital mechanics experts have already laid out a theoretical mission proposal. Their concept involves launching a spacecraft during a specific window between 2027 and 2029 using a Venus-Earth gravity assist maneuver. This technique uses a gravitational pull of planets to accelerate and redirect a spacecraft, allowing it to reach distant targets without requiring excessive fuel. According to their calculations, using these planetary slingshots, a spacecraft could reach BB around 2033 or 2034, just after it crosses the ecliptic plane. That would be a remarkable opportunity to intercept BB when it is still relatively close, still actively sublimating, and possibly showing unpredictable behavior. Unfortunately, there is no official mission in development. This stands in contrast to another major opportunity that was also missed: the chance to redirect NASA's Juno spacecraft toward 3IR Atlas, the suspected interstellar object currently generating significant interest. Juno is already orbiting Jupiter and nearing the end of its mission. At one point, astronomers suggested retasking it toward 3IR Atlas for a close flyby. But due to late planning and logistical limitations, that opportunity passed. Juno will be decommissioned in Jupiter's atmosphere instead of being reproposed for a groundbreaking interstellar encounter. BB presents a similar, yet much larger, opportunity, possibly even more significant. Unlike 3IR Atlas, which is relatively small and fleeting, BB is large enough to study in detail. It has gravity, complex chemistry, and potential to reveal how material from interstellar space interacts with the solar environment. It may even help answer fundamental questions. How did the solar system form? What kinds of objects brought water, organics, and minerals into planetary systems? Are there cosmic building blocks that predate planets themselves? A mission to BB would not be just another comet flyby. It would be a journey to a time capsule, a frozen survival of the solar system's birth, untouched and unchanged for perhaps 4 billion years. We could analyze isotopes, measure surface chemistry, study how volatile ices behave at Saturn-like distances, and possibly even understand how gravity, heat, and ancient ice interact in massive comet-like bodies. Space travel is not just about exploration, it is about timing. Objects like BB do not appear often, and they do not wait long. If we miss this chance, we may never encounter another object like it in our lifetimes. For now, BB remains unvisited, unmeasured, and uncharted, a silent messenger passing through our region of space, waiting for someone to reach out. See, our 2014 UN 271 Bernardinella Bernstein is not proof of alien technology. It does not display artificial structure, propulsion, or any indication of intelligent design. Yet, it is also not something ordinary or easily dismissed. It is a rare and extraordinary visitor, not because it is artificial, but because it is profoundly natural in a way that challenges our understanding of how objects behave in space. BB is a reminder that the most astonishing things in the universe are not necessarily made by intelligence. They are made by time, gravity, and the silent laws of physics that existed long before us.